Welcome dear students. Today our lecture is about mass transport in unsaturated and saturated media. Mostly we will be focusing on saturated media, how the water is flowing in different geological formations. At the same time, we will also try to understand the phenomenon, how the solutes are being transported along with the water. Because we have a variety of geological formations, and every geological formation behaves differently based on its texture and based on its physical characteristics. Sometimes we have uniform texture, sometimes we have sorted out texture. Both will be having different kinds of behaviors. And if there is some interlocking uh, between these different soil fragments, it will again hinder the path. So finally, we will have to what kind of transport physical processes do exist and how they can be demonstrated or worked out for their quantity and for their velocities in along with the groundwater. Next, we will again it's a kind of revision. We have already gone through it. Conservative and non-conservative solutes, what are they and how they behave. We were discussing it last time. I think it's quite clear as today we are going to use this phenomena in our physical processes. So basically, focus here. This is the CS, which is giving us the mass of contaminant in unit mass of soil grain. And how it is existing, it's quite possible that this CS is attached with the solid phase. So the concentration of contaminant solute held adsorbed on the solid phase will give us the contamination level which will be retained, which will be existing and staying within the within that of soil. But if it is reactive, if it is getting dissolved in water, if it is getting reacted with some other minerals or ionic conditions, ionic radicals, in that case it will be changing its formation and it will then mixing with the aqueous phase of water, and then it will behave as a solution, and that solution will based on the geological structure and formations. But this is going to retain within the soil. It is not going to move forward. So when we are going to talk about this concentration of mass, uh, in that case, we will be comparing this mass of contaminant with respect to the mass of the soil. So the units which will be used in this case will be milligrams per kilogram. While in the previous case of this non-conservative solutes which have reacted and which have mixed with the water phase, then it will be declared as concentration. And then that concentration, what are the units of concentration? Milligrams per liter. So this is something which is existing in the aqueous phase. This is something which is existing in the solid. So it is kind of the same description. Here you can see the CS, mass of contaminant in unit to mass of soil grain, gram per kg or milligram per kg. Non-reactive or non-biological chemical reactions, no affinity for solid phase. So these are the ones which are not going to react and they will be sustained. So again here we are talking about different scales. I think we have talked about it earlier as well. And, these are the contaminant properties for flow. So obviously the mixing with uh, with the water, the density of the water, and we also talked about the significance of this. Okay. So these are the physical processes control flux, and if we talk about this, uh, these are having three formations: advection, diffusion, and dispersion. So solutes carried along flowing groundwater will be expressed as advective movement, and it will be totally based on the groundwater flow. So being in the aqueous phase, the solute is supposed to move along with the water. Very simple. In diffusion, we are having some restrictions of the water movement. It's quite possible there is some uh, interlocking, and because of that, the water is being stuck in some geological formation, and because of that, the only mode of transport is the diffusion. How diffusion works out, it is based on the concentration gradient. So concentration from higher to lower will obviously shift uh, the balance, the equilibrium, and in the dispersion we have some transport by mechanical mixing. And what is this kind of mixing? It is completely dependent upon the geological formations. So longitudinal dispersion and long, uh, uh, movement along the uh, length, movement along the depth, movement along the cross section, longitudinal as well as latitudinal movements would both will be considered in this case of dispersion. And in this case, while discussing with this, we are also concerned with the uh, change in the layers. So when the layers are changing, obviously the that it is the actual texture of their soil is changing, because one layer will be differentiated from the other layer based on its texture as well as its formation. So quite possible it has a very uniform distribution of all the particles. Next layer is only consisting of sand. Next, the third layer is only consisting of silt, and the fourth layer is only of clay. In that case, uh, all the movement is totally based on the dispersion. So it has nothing to do with the groundwater flow or this concentration gradient, but it will only follow the dispersion of the uh, dispersion levels of the uh, so it will be having different kind of scenarios for all the different layers. This is again kind of repetition. This is the mechanisms. So while moving along the water, we are already having some kinds of reactions taking place. Biological processes are taking place. Chemical processes are taking place there. So all these are having uh, some reaction. So that reaction makes the solute reactive. So in as a result of that reaction, it is quite possible that solute is going to change its chemical nature. So quite possible that the chromium hexavalent will be converted to chromium trivalent. Uh, so gaining some electrons and by the process of reduction. Similarly, some other oxidation reduction processes can take place. So there is quite a variety of things going on within these file structures. So all depends upon the soil characteristics. That's why at the same time we will be having some this kind of reaction as well, which is advection, which is totally based on the movement, and dispersion totally dependent upon the geological formations. While this movement is totally dependent upon the processes, chemical, nuclear, biological processes. This is something which is going on in our subsurface. especially in porous media. These activities are on high level because in the soil in the unsaturated zone, we have already limitized and constrained and restricted the solute with the soil particles. So again, it's kind of repetition and we can go through it. Well, here, average linear velocity Vx is the rate at which the flux of water across the unit uh, cross-sectional area of pore space take place. It is also a part of the Darcy law, which we discussed in the previous lectures. We came to know that this average linear velocity Vx is actually the flux which is making the water to flow. And how this can be determined? It is actually the hydraulic gradient, uh, the conductivity, and then the hydraulic gradient. Both are responsible for this kind of move to the next point. The effective porosity Ne is the porosity through which the flow can occur. And this is something which we talked when we were discussing this average linear velocity, which is the actually taking place, the flow which is actually taking place. This is the hydraulic conductivity, and this is the hydraulic gradient. Both will be multiplied, and this factor is giving us giving us the porosity which is effective, which is only accounted for the connected interconnected pores. And then amount of solute transported is equal to concentration multiplied by the average linear velocity. This is the average linear velocity Vx k dh by dt, and Ne is the effective porosity. This Ne is making it average linear velocity. Otherwise, it will be Darcy velocity, where Ne is the effective porosity. Therefore, advected contaminants move at the average linear velocity. Obviously, the contaminant is supposed to move along with the water, and that's why it will be ending up with the flow of groundwater, whatsoever the velocity it is attained. It has attained. So there is something about the mass flux, and it is actually the change. So flux is actually anything which is changing with time and with location, and can be associated with any kind of parameter. It can be mass flux, it can be volumetric flux, it can be density flux. So while talking about the movement of water in a typical direction, we can determine the flux in mass. So what's the mass? Mass is only related with the contaminant solute. So when the solute is moving along with water, how we can determine its flux? So this is the expression. In the previous slide, we worked out the concentration multiplied by the um, average linear velocity. It will be giving us the mass flux. So if we are going to determine it here, we will be finding it Fx is equal to Ne Vx into C. Ne is the porosity, Vx is the average velocity, and then F is the advective mass flux is equal to total mass of solute which is carried across a unit area oriented normal to the bulk fluid motion. So this is actually giving us overall scenario for the advection and giving us some expression for the mass flux. And mass flux, the mass of solute flowing through a cross-sectional area of soil, including solid phase per unit time. Cross-sectional area available for seepage is equal to N into uh, differential area, and it will will be less than the total cross-sectional area. So how it will be reduced? Because this n is a ratio and it will be in the form of points, and it will be only considering the area which is playing its role in the movement. And obviously, if we take the total cross-section area of that flowing channel or assumed channel, in that case, obviously, this area will have lesser value, and as compared to the total value which is having an overall movement and overall cross-sectional area of the channel. So it will be obviously lesser. So lesser the volume, lesser the area, higher will be the velocity. Higher than the torus velocity, which is ideal velocity. This ideal velocity is considering the whole cross-sectional area, while average velocity is only considering the area with this effective porosity. So this is the basic difference which must be kept in consideration. Now, this is something about the electrokinetic effects which are taking place within the soil. Uh, so, for example, we have a clay surface here, and then inside our channel we have every kind of solute. So these are the solutes. If you observe that the positive ones will be much nearer to the clay so that they can have an interaction, unless they have already dissolved in this water. So anions and these are the cations. These are available in our channels. They are actually playing its role in getting retained or getting dissolved. Both are the cases. If we have a clear layer here, it will obviously generate the positive particles on the sides of the channel. Now this is something about the diffusion solute in water moves from area of higher concentration to lower one, and the mass of fluid diffusing in proportional is proportional to the concentration gradient, which can be expressed as Fick's first law in one dimension. So this is the application of that Fick's law. This is the concentration gradient. So this is the x is the gradient of the gradation, and this is the diffusion constant. So this is going to give us how the mass flux is taking place with due to the diffusion process. Earlier we worked out mass flux when the movement was advective. Now we are finding out the mass flux when we have only diffusion. So diffusion uh, is only considering this concentration gradient as the movement. Molecular based phenomena and net movement towards area of lower concentrations. Mass flux per unit area per unit time. dd is the apparent diffusion coefficient in soil concentration, and this is gradient. Again, it is the simplified version, and it will be declared as the uh, uh, first law. So obviously it will be negative because it is reducing. Then we have another uh, uh, law, that is Fick's second law, derived from the Fick's first law and the continuity equation called diffusion equation. So this is the partial Ca by partial T. Now actually what we are doing here, we actually finding out the change in concentration and with reference to time. And in that case, we are taking a double derivative of the concentration gradient. And this time our diffusion coefficient is also further based on this differential part. It can be expressed here. Well, we will talk in the next slide, and it is kind of again this summary and kind of repetition here. Fick's first law is this one, and D was the diffusion coefficient, chemical gradient is the driving force. So I think it is easy now to understand what's going on in the soil, because uh, different kinds of behavior take place, because a variety of soil formations, geological formations beneath the subsurface. Everything is going to behave. As a result of that, uh, it all depends how the water will carry that contaminant. Initially, in our first one reaction, it was all because of the movement of the water that the contaminant is moving. Then it is because of the this diffusion, and then again we will check it's because of the dispersion. So what we are doing out, we are doing only to find the mass flux, the change in mass. It's about from one point to the other point, how from one location to another location, direction is changing. For example, within 1 meter distance, within 100 meter distance, within 1 kilometer distance. So as far as we go, our phenomena is getting complex, because we have more and more variety of the soil textures. So every phenomena is going to behave differently. While we are working on our contaminated side, we need to incorporate all these changing phenomena from one point to the other. So we will have to check at what point the concentration or the mechanism is changing. So this will derive our differential equations. And normally, if we are doing some model, we are having some simulation facility, we can easily make we can easily make different components for each layer, because each layer will behave similarly, but different layers will behave differently in a given cross section area. So, for example, if we have 1000 meters to be investigated, we can divide it in most suitable cross sectional areas, how far we can go, and how easily we can divide it into those segments which are similar in their characteristics. So not only in the horizontal direction, meters to 1000 meters, but also in the depth wise vertical distance as well. So for example, we have 100 meters down in vertical direction, and then again in this 100-meter we can again have a variety of soil formations, and we can divide the vertical cross sectional area in different layers. So every layer will behave differently. So first of all, we have longitudinal, we have latitudinal movement. So similarly, the dispersion is also longitudinal as well as latitudinal dispersion. So it's all about the understanding and getting the most suitable cross-sectional areas, most suitable layers, which are actually behaving similarly in a similar manner, so that we can apply a similar equation for that typical cross-sectional area with the same properties. So it will help in getting a simulation which is more nearer to the reality. So if we are having some contaminated site, we must work out the variations in concentration in not only in the mass of solute but also in the uh, physical conditions, the geological conditions, which will actually um, uh, lead to a proper decision what kind of equation we need in that particular cross section. So it will help in simulating the whole study area of the contaminated site. If you begin working in continuation, and if you have what important thing is here is this tau here, and this tau is actually tortuosity factor. So tortuosity factor is included in this diffusion coefficient, and this Tm is equal to the effective diffusion coefficient. So length of real path is L, and this tortuous path is Le. If you find it here, then we have transport by concentration gradients, and we have already gone through it. Fix first law and fix second law. So first law is for movement of through diffusion from one to the other point, while fix second law is the concentration variation with time. So this trusty, as it is very obvious, it's because of the effective length, and it depends upon the structure. I think you can go through it. Now it is again another important process, physical process, which we earlier talked as well, and it's mechanical dispersion. If you see these figures, in this figure you see that this movement is moving variation of chemical concentration gradient, and this movement is quite facilitated with the gradient movement. Here the concentration is higher, here the concentration is less. And similarly, in this figure, you can see the velocity distribution. The central line is having velocity, while the other uh, uh, these lines of flow, which are adjacent to the soil volume, uh, soil contained channel. In that case, it is because of the friction. First of all, that it is quite uh, lesser velocity on the sides, while in the middle we have a smooth flow, and then it is facilitating the fastest track of the flow. Similarly, here you can observe that the movement is based on the geological structure. So this geological structure is actually guiding the movement process, movement physical process. So it's not being uh, guided by these velocity gradients, change in velocities, or some advective movement, but neither with these physical processes, but it is actually due to this availability of the path. So on this side, it is easier to move this way. For this central line, it's easier to move in this way, and then for this end, it will be easier to move this way. So this is called mechanical dispersion. And at the same time, we can have these three phenomena occurring together at a stage. But if we are considering them, we are considering them separately, and so this is something which is about the mechanical dispersion. When we talk about mechanical dispersion, um, we are going to have this change, which is led by the mechanical dispersion coefficient. Now, this mechanical dispersion coefficient is very important to be understood. So, this mechanical dispersion coefficient is actually this alpha into this v, and this v is actually instantaneous velocity. So, this instantaneous velocity multiplied by the longitudinal dispersion is going to give us this mechanical dispersion coefficient, and it will be multiplied by the factor of the porosity, and then we will be having a change in concentration. This is going to give us the how gas flux is taking place. So this is alpha L, heterogeneity of medium, and heterogeneity is something changing from one point to the change in characteristics from one point to we are having a variety of the geological formations. We will be having a more heterogeneous. If we have a more heterogeneous medium, that means the value of this alpha will be higher because it will give us a more tortuous path. So what actually we are concerned with the ease with which water can flow. And if we are having a tortuous path, it will make the movement more complicated. So what will be the leading factor? It will be the particle size distribution. Particle size distribution is actually based on the grain size of that soil texture and the spaces between those. This is something which is related to this uh, dispersion, and this is the distance between the two medium, and it can have the movement, facilitate its movement because of it, this distance. Scopic scale, and again this D50 is the grain size, and for macroscopic scale we have this much conditions that alpha L will be almost equal to this length, and this length of this horizontal dispersion or depth-wise dispersion. It is actually not depth but the distance between the two medium. So again, this is some description. I think you can go through it. Mechanical dispersion is AL multiplied by Bx. AL is a factor called dynamic dispersivity of the material, and Vx is again the linear velocity. Some of the retarding factors. So these retarding factors are actually sorption. And what is sorption? It is sorption is the process of absorption with the solid phase. And if we the target of being the target of working out a contaminated site is to decontaminate the site from the contaminants. In that case, we need to uh, detach this contaminant from the grains, soil grains. That process is called desorption. And so, if we are going to solve out the problem of the contamination, we need to desorb. So, desorption are two processes which are important to understand while we are talking about movement and of the attachment of contaminant and its treatment and its removal from the soil, contaminated soil. We will work out, we will determine this process when we will be talking about the uh, treatment of the contaminated site. Number is an important factor to determine how this dispersion is efficient. Relationship between the different uh, dimensions and different diameters. The convenient ratio that normalizes dispersion coefficient by dividing by the diffusion coefficient. So VDM over DM is called a Piglet number and E a dimensionless number. So if we have this Piglet number, it will give us the ratio on which this dispersion is taking place. So whether it will be diffused or it will be dispersed, both phenomena can take place. For diffusion, we have this coefficient, and for dispersion, we have the other coefficient. and both coefficients are interlinked. And this phenomena is this ratio between these two coefficients will give us the value of Piclet number. Piclet number will define how this cross-sectional area of this layer will uh, will exhibit its behavior. It's all dependent upon the Piclet number. We will not go into much details, but here is a combination of the processes. Initially, we worked out all the processes individual basis just to have an understanding. But if we consider an real based scenario, it is actually a combination of all these processes. All these three processes can take place simultaneously at one time at one place. This is the total mass flux of a solute, which is considering all these fluxes, advective, diffusion, and this dispersion, chemical dispersion. All these things are included here. This is giving us a comprehensive, complete equation which we are incorporating all our mass flux equations, and then we are simplifying it and trying to find out what the coefficient, combined coefficient we can develop. And then again, this is our model. Considering one box, volumetric box, in which all kinds of flux will be incorporated, and this representative volume will actually behave like a system. So this system has something coming inside and something going outside of this system. Some processes are taking place inside which are consuming the influx and it is affecting the outflux. And at the same time, we can understand that all the contaminants within this box can have some reaction. So the influx of the contaminant will not be equal to the outflux of the contaminant because of the utilization within this process. So the rate of solute mass increase within this volume, this representative volume, will be described as solute mass flux into the box minus the solute mass flux out of the box, and then increase or decrease of solute mass due to various reactions taking place in this box. So this box and this slide is actually the fundamentals of our modeling and our all the simulations which we will be doing for the purpose of groundwater modeling and contaminant transport modeling. Everything will be based on this equation. So just remember and memorize this equation for your use. So these are some other things which we can go through, and I think it will be quite complicated and we will not talk about it today. We will be finishing our lecture here.